Welcome to our paper on reinforcement learning with rare significant events, where we compare two state-of-the-art policy search methods, namely CMAES, a direct policy search method, and PPO, a gradient policy search method. Our goal is to understand the behavior of each method when significant events are rare. Significant events are the only events where a non-null reward may be obtained, the magnitude of the reward being dependent on the agent's behavior at that particular moment. Here, you can see an illustrative example with partner choice. The blue agent faces several possible partners, some of which will never want to cooperate, and some other that offer different level of engagement. The goal for the blue partner is to pair with the partner that offers the best engagement. The challenge is for the blue partner to offer large enough engagement so that it can be chosen in return, but not too much, as energy should not be wasted. The partner choice problem can be formulated as a reinforcement learning problem as follows. The goal is to learn the agent policy parameters theta so that it gets the best return value over a limited amount of time, which in this case will be the unique positive instantaneous reward the agent gets, or 0 if no successful interactions occurred in the allocated time. It is important to notice that an episode stops after the first positive reward is obtained or time runs out. The instantaneous reward depends on the agent's action at a particular state S. However, some states may never lead to a positive reward, whatever the agent's action. These are the non-significant events. On the other hand, significant events may occur with a probability of P, where the agent's action may or may not lead to a positive reward. It is thus important for an agent to choose its action wisely when significant events occur, possibly refusing uninteresting opportunities if it hopes a better one may be presented in the future. We compared three algorithms: a direct policy search method CMAES using a multi-layered perceptron, and a gradient policy search method using PPO using a multi-layered perceptron. Also, both are using the dimensions of 30 weights. Then we also use PPO again using a deep neural network with more than 100,000 weights to possibly benefit from over-parameterization, which is typical with deep neural networks. The left figure shows that CMAES outperforms both PPO variants in terms of both performance and speed of convergence. Even more, CPU time for CMAES is lower than PPO, as it does not need to compute gradients at each time steps. Also, we can see on the left figure that the rarer significant events are, the less efficient PPO is, which is a problem that is not encountered with CMAES. The take-home messages from this presentation and from the poster is that first, the direct policy search, at least with CMAES, fares better than policy gradient search with PPO, with rare significant events, as CMAES is not affected by non-significant events, while gradient search actually suffers in that case because many gradients are not meaningful. CMAES also does not need large neural networks, while PPO fares much better with over-parameterized neural networks, which can be expected but also requires a larger cost in terms of computation. Another conclusion and take-home message is that small neural networks should always be tested as control experiments when using evolution strategies. If you are interested, please come and see our posters. You can also go on archive to read the full paper, for which the QR code is accessible on this page. Thank you for your attention.